All right, very good. So let's see. The office hours will be held in the yellow room. And we have pens. In the yellow pen. Anyway, it's just our little gathering space up there on the southwest corner of the second floor. Okay, we'll be there hanging out, having a cup of tea, and taking your questions and your coffee. All right, I'll be there too. All right, so last time we quantized the field in the Coulomb gauge, which is the standard way we do it in quantum optics. It's not a Lorentz invariant gauge, but we don't really care. That's not important for us to write a manifestly. I mean, obviously, physics is still Lorentz invariant. It's that the gauge choice depends on the reference frame. And we stay in a particular reference frame, and we're happy. Okay. So we then, in that Coulomb gauge, which is also known as the radiation gauge, we set the divergence of the vector potential to be 0. And so the field we quantize is the part that is transverse. That is to say, the part that has 0 divergence. The normal modes we choose typically, although not always, but it's the simplest thing to do for thinking about the free field, is that we imagine a quantization volume with boundaries towards infinity, and we take periodic boundary conditions. It's a way of us discretizing the modes into a countable set. So we look at plane wave modes inside this quantization volume with some polarization vectors that have to be transverse to the wave vector, right? And these are a set of orthonormal modes, and they are complete in the sense that if I sum over all, sum over all the modes, that I get this so-called transverse delta function. If I didn't have this over here, this would be a delta function, right? The familiar delta function in 3 dimensions. And then I would just have the unit dyadic representing the unit tensor for the polarization directions, right? It would, if I looked at the components I and j, this would be, the unit would be a Kronecker delta ij, right, if it was. But the fact that we're only summing over the modes that have 0 divergence means we have to subtract off the piece of the tensor that's along k. And that's known as the transverse delta function. Okay? And it's an exercise to try to show that this is true by substituting in those modes, okay, and doing that integral. All right, so with our normal modes, we can then, yes, sir?
Is the, of that second thing that subtracted off the identity
Yeah.
operator, is the ij operator kij?
That's correct.
Okay.
That's correct.
So it's a full 3x3 matrix.
It's a 3x3 matrix, that's correct. Yeah. For the 3 directions in physical space of the vector field. This is, since this is a vector field, the modes are vectors, this is a dyadic or a tensor. Right, okay, so with that, we then wrote down in our standard way the decomposition of the field, the vector potential in terms of the normal modes, with some characteristic units that we ultimately derived. Okay, so this corresponds to annihilating a photon in this plane wave mode. Okay, and then there's the conjugate term, which has the A dagger, which I wrote out explicitly here for the case of the electric field. So there is a part that has the annihilation operators and the part that has the creation operators. Okay, and this is the characteristic scale of the electric field is understood given a photon that has energy h bar omega. The electric field associated with that photon is the square root of h bar omega over the volume in which it's confined. Okay. You might ask, what if we don't really have a volume? I mean, you know, this was a fictitious volume in the first place. This was a quantization volume that was there as a mathematical tool. How would we associate an electric field to a photon in that case?
That being one.
Yeah, then so, you know, it's a tricky question, actually. Really, one would have to think about a photon wave packet in some sense, localized in some 3D space, but then it doesn't have a definite frequency, right? Or a definite energy, if I were to keep it, if I were to localize that, right? In three-dimensional space. In free space, the energy eigenstates are completely delocalized. So really, it's an undefined question. We can think about the electric field of a photon in a pulse, or maybe something related to its coherence length if it wasn't. But for a monochromatic field, really, there is no, the electric field would be zero if it was completely delocalized over all space. Okay. And then we have the magnetic field, which is similar to the electric field, except the direction of the magnetic field is related to the cross product between the direction of K. K cross E is B, right? And the usual E cross B is K. So this is the direction of the magnetic field. Of course, E and B don't commute. Nor does any of these other fields. You can check for yourself. So when we think about states, quantum states of the electromagnetic field, we cannot have states which simultaneously have well-defined electric fields and well-defined magnetic fields. This is a kind of relation of similar to the uncertainty principle. There are quantum fluctuations always in the electromagnetic field.
Is it a commutation or?
Oh, no, sorry, does not, I meant does not.
Okay.
Sorry, yeah, I meant that, but I wrote that. Yes, thank you. Right, we're going to talk more, though, about the nature of, in what sense, we're going to talk in a few weeks about states of the quantum electromagnetic field that most closely resemble or have the properties of what we think about as classical fields. When we think about classical electromagnetic fields, somehow that has to be described by QED. That somehow has to come out of QED, what we call classical electromagnetism. In fact, that's how I ended up in this business in the first time. That puzzled the heck out of me as a first-year graduate student. What the heck did, you know, electromagnetic waves have to do with photons. I mean, you think about photons, they kind of are little particles, you jump, and, you know, where the heck did that come from? And so, as a first-year graduate student, we had to write a paper for E&M, and as our final project. And I chose as my topic the classical limit of quantum electrodynamics, and I discovered these lecture notes by a guy named Roy Glauber, who is the father of our field, quantum optics. And we will get to distribute. They were like, it was like, you know, the pearly gates of heaven open. Reading those notes, it's like you see someone who has incredible insight and can explain things with such clarity. It's just a piece of beauty. And that's how I ended up going. I was going to do plasma physics, but God forbid I. Anyway. All right, my little story. In writing this down, we then said if we wanted to look at the Hamiltonian of the field is just the total energy in the electromagnetic field, which is the integral over the quantization volume of the energy density in the field. And if we plug in these relations, what we find is this is the sum over the modes, h bar omega, n plus a half, n being the number operator for each mode, right? What about the momentum in the field? What is the momentum in the electromagnetic field? You guys remember?
It's K times A.
So if I were to ask, what's the momentum, total momentum? Electromagnetic waves carry energy. They also carry momentum, right? And the momentum flux is related to the Poynting vector, right? So the total momentum in the field is the integral over all space of the Poynting vector over c squared, which in CGS units, the Poynting vector is c over 4 pi e cross b, so this is 1 over 4 pi c e cross b. And if I want to know what the momentum operator is, it's this. So that's the momentum operator for the electromagnetic field. And is your homework assignment, should you so choose to attempt it, to show that when you plug in our mode decomposition, that this is equal to the sum over all the modes, h bar k, a dagger a. So, what we take away from this, of course, is that the photon has in mode, in a plane wave mode, has momentum. And that momentum is h bar k. So that's, of course, to be expected. We know that the plane wave states in our first quantization picture are the eigenfunctions of the momentum operator. And this is the second quantized version of what we would have in first quantization. We're going to come down over here. The momentum operator, well, I can write it in in the position representation in terms of the gradient, or I can write it in the momentum representation. And the second quantized version just says, this is the eigenvalue, the operator, of course, in this case would be, have a it's multiplication by this in the momentum representation, and its derivative in the position representation. And the second quantized version says for every photon in that mode, you have the number operator. What about the angular momentum of the photon? Well, that's complicated. As we know, there's two flavors of angular momentum. There is orbital angular momentum, and spin angular momentum. Now, classically, the total angular momentum in the field, again, depends on the Poynting vector. It's the cross product of the position with the Poynting vector in units of c squared. Okay. Which is so, as you have studied in your electromagnetism, I hope, the electromagnetic field has angular momentum as well, and that's the total angular momentum. But we can decompose that in terms of a component that has to do with the rays, what we would call the orbital angular momentum, and something having to do with the direction of the vector, which in the quantum world becomes a spin angular momentum. And as you so choose, you try to do this in your homework, and you find the following. The spin angular momentum component of this is equal to the following. So, the total spin angular momentum operator for the electromagnetic field involves, in this decomposition, we've chosen a particular set of modes. They're plane wave modes which have either a positive or negative helicity. So we're looking at plane waves which are propagating in some direction, which is specified by that unit vector. E sub k is the direction of the wave vector. And then we can have two helicities. We can have positive helicity, which corresponds to right-hand circular polarization relative to the propagation direction, or negative helicity, which corresponds to left-hand circular So we've chosen a particular set of modes, and for this particular mode of decomposition, the spin angular momentum operator for the electromagnetic field has this form. How do you interpret that? Maybe now you can interpret it.
It's like the second quantized form of our good old friend.
Which friend?
Uh,
I got lots of, well, I don't have that many friends. I have some friends.
Well, all our friends in the beginning of the semester, we would have like those bra and cat
Bras and cats, yeah.
things. Which are
Kind of like, yeah, so you can think about this as a kind of a plus and a minus, that kind of thing. All right, I kind of like that. This is kind of the second quantized version of this first quantized thing. But what physically does this tell me?
The total amount of angular momentum and the positive velocity.
So how much spin angular momentum does a positive velocity photon have? 1 unit of h bar. It has h bar, right? 1 unit of h bar for positive velocity, and -1 h bar for negative velocity. Okay. There, of course, 0 h bar would be there. You know, that term doesn't show up because it has 0 h bar, right? However, so what we say is that photons in these modes, if I have a photon that is prepared in one of these modes, it has a definite spin angular momentum projection. The projection of spin angular momentum along K eigenstates that have a definite spin angular momentum relative to the direction of propagation. Okay. And we either have +1 h bar along K, which corresponds to the polarization vector rotating with the right-hand rule like that, or we have -1 h bar if the polarization is rotating like that. What if the polarization was was linearly oscillating along this axis?
Superposition.
It's a superposition of definite angular. That photon doesn't have a definite projection of angular momentum. Okay. Now, one of the things that is important here, the fact that I have only these states is, say, I can only talk about the eigenstate of spin angular momentum along K. This is different than we think about when we think about the spin angular momentum of an electron. When we think about the spin angular momentum, for example, of an electron, we usually think about a quantization axis, which is space-fixed. It has nothing to do with the momentum of the electron. We just choose some direction in space, perhaps chosen by a magnetic field, and we call that the z-axis, right? And so we have some axis, and we can think about the projection of spin angular momentum along any direction we like, which could be the quantization axis. And there are eigenstates, and there are 2j+1 different states with definite projection of angular momentum along that axis. But that's not true for the photon. There are no eigenstates in general that we can define relative to some space-fixed axis. We can only define that are eigenstates of the momentum dotted into the spin. Why is that? Well, it's a complicated business, but this is intimately related to the fact that the photon is massless. Now, what the heck is the connection between the fact that the photon is massless and the fact that I can only define good eigenstates relative to the momentum and not relative? This is a body fixed. The body of the photon has some momentum, and I can only define it relative to its momentum, not a space-fixed axis. Yeah, ma'am.
Because it has to be traveling since it's massless and it has to be traveling at the speed of light.
So it's obviously related to that. The fact that it's massless means that it's traveling at the speed of light, which means that I cannot go to the rest frame of the photon. If I could go to the rest frame of the photon, in the rest frame of the photon, its orbital angular momentum would be 0. And I can say the generator of rotations in that case would just be the spin orbital, the spin angular momentum. Remember that the angular momentum operator is the generator of rotations. And if I can go to different reference frames, I could separately rotate the direction of the spin different from the direction of the orbit, because in a different reference frame, I can make one of these 0. But because I cannot go to the rest frame of the photon, I cannot turn the direction of the spin into different from the direction of the orbit. They're locked together. And since I know what they are in the lab frame, that's the same in all frames. And that's the reason why we only have, even though it's a spin 1 object, we only have 2 good polarization states. It looks like a qubit, which we could map onto the algebra of a 2-level system, which is like a spin 1/2 particle, but the photon has spin 1. That's the answer to a puzzle that Sam raised away at the beginning when we were asking, well, what the heck is going on? We had the point of the fact that we had to we mapped the polarization states, as you did in one of your homeworks, onto a qubit, yet the photon is spin 1. Great. All right. Yes, I'm listening.
So even though photon has visibly only 2 states, we know it's a boson because of statistics.
That's correct. That's correct from its statistics. Also, I mean, we were able to, I mean, all of this is consistent with measurements. We know, of course, if we look at the angular momentum conservation in terms of absorption and emission of photons from matter, that the amount of angular momentum that's imparted is 1 or plus or minus 1 h-bar. You can either absorb or emit h-bar. If you absorb on a transformation, does it give you orbital angular momentum? That's another story. So empirically, we see these facts. Mathematically, we used commutation relations in our definition of our field that is to say these A's and A dagger satisfy commutators, because the vector potential is a three-component field, and therefore it is a spin 1 object. So it's all consistent with the symmetries that we know, and empirically all agrees. Now, it's not an arbitrary spin 1 because of this constraint, the fact that del dot A is 0 is intimately related to the fact that the photon is massless. Yeah.
So, if I think about this as like, you know, U vectors of SU2, which one am I looking at? Am I looking at the three-dimensional?
No, we're looking at something else, which is called the Wigner-Little group. That's a more complicated story, which is intimately related to, so there's a different rotation group, which is known as the Wigner-Little group. Now, if I fix the mode, let's say either the propagation direction, or as we'll discuss, the mode in the cavity, I can still restrict dynamics as we did in the homework. For example, define a pseudospin corresponding to 2 photon states. It's not related to the fundamental symmetries of the electromagnetic field, but I can always, if the system is restricted to 2 orthogonal states in the Hilbert space, then that maps onto a pseudospin, and I can think about SU2 transformations in that Hilbert space. They're not the fundamental symmetries of the field, which were related to this, but it's the transformation we would use with the wave plates and phase shifters and all the rest. Yeah?
So now that we're considering the angular momentum of the photon, do we have to start including that in our atomic picture as well?
Oh, that's a good question, Matt. That's a good question. So actually, what the heck? Let's talk a little bit about it. This is a little bit of here's a little puzzle for you. Okay. Do you guys, is the solid angle impossible for you to see this part of the board? No, it's okay. I can't really tell what the glare is like. I'm curious. All right, let's say I have two energies with sublevels. So I have a ground state, which is an S state, and an excited state, which is a P state. Okay. Now, when we define these Zeeman sublevels or magnetic sublevels, we're doing that with respect to a space-fixed quantization axis, right? So when we define this to have the M, the magnetic quantum number, the Zeeman quantum number, to have these +1, -1, and 0, we're saying the atom's angular momentum there are eigenstates which are +1, 0, -1 relative to some axis that I'm calling the z-axis. And that's a space-fixed axis. It has nothing to do with the momentum of the atom. It's some direction that we might fix with a magnetic field and say break this degeneracy, but we don't have to. We just think about it as some direction we choose. It's a coordinate system, okay? Now, we know that I can drive transitions. These are all allowed electric dipole transitions, right? And we say that this one corresponds to pi polarization, and these correspond to sigma polarization, which are typically called sigma plus and minus, having nothing to do with the Pauli operators, nothing. It's just a different use of the word sigma plus and sigma minus. Okay? So what do these mean? Well, what it means is if I have some axis I'm calling the z-axis, these correspond to the, if the atom is in one of these states, then, if this state has +1 of h bar angular momentum along this axis, this has no angular momentum along this axis, this has -1 h bar of angular momentum along this axis. Okay? Now, that angular momentum has to come from somewhere. I start with the state that has 0 angular momentum. And so if it ends up here, it got 1 unit. Where would that come from? It would come from the photon. How could that happen? Well, if I had a propagating photon that was propagating along the z-axis, and it was rotating like that, then this photon would be absorbed and the atom would end up in that state, right? On the other hand, if it ended up in that state, it would be propagating along this direction, for example, and going the other way, right? Then this would be a positive helicity would correspond to this guy, a negative helicity would correspond to this. But how the heck can I generate that one? Okay, so how would the light, what kind of light, what's the mode that could drive this transition? Okay, so let's say I'm propagating here and have linear polarization. Would that do the job? I see some, no, why not? That's a superposition of this. That would drive the atom into a superposition of these two modes. So how the heck can it get there? The photon can't propagate along the z-axis. It has to, if my photon were propagating like this, and it was linearly polarized, well, it's a superposition of plus and minus helicity relative to this direction, but it has 0 angular momentum along the z-axis. So this is something that laser physicists often get confused in my experience about what we mean about pi sigma plus sigma minus relative to right hand, left hand, and linear polarization. Pi plus and minus, sigma plus and minus are relative to the space-fixed axis. Whereas helicity is defined with respect to the body-fixed axis, the body of the photon. So, question for you. Suppose the light that I sent in here was right-hand circularly polarized. But I'm choosing the quantization axis like this. What transitions would I drive in the atom? I would drive, this guy is a superposition of this and this coming out of the board, right? It's a superposition of pi and this. But this is a superposition of this and this. I would drive all 3 of these transitions, right? Because the sigma, so pi is along this direction and sigma is along that direction. Anything perpendicular to the quantization axis, who knows what the word for perpendicular is in German? I don't either. It starts with an S, and that's why it's sigma. And so anything that is perpendicular to the z-axis is sigma polarization. And if it's linear, it's a superposition of this and this. Okay? So you have to define, you would have, this is the z, this is x plus iy, and this is x minus iy. And if I had linear polarization, or I had circular polarization like that, it would be Z plus I X, for example. Right? So I have a Z component, and then X is a superposition of these two. So I would drive all three. That's into some superposition of all three. Now, of course, what that means is the atom's angular momentum would be rotating relative to the y-axis as a circular. But something rotating with respect to the y-axis circularly is a superposition of all three directions relative to the z-axis. So you have to be very careful about the space-fixed directions versus the body-fixed directions. Now, one last thing, because we're on a roll here. What if I had not a p state? Remember, S states are L equals 0, p states are L equals 1. That's a p. What if I had a d state? That's an L equals 2. And I started in an S state. That's not a dipole allowed transition, but it isn't completely verboten. I know how to say that in there. It's an allowed transition, but it's an electric quadrupole transition. This state, I can drive it. It will take, in fact, I can go from here to here. That's a possible transition. I started with 0 projection of angular momentum along the z-axis and up with 2 units. How the heck can I do that? The photon only has h bar omega. I mean, 1 h bar of spin angular momentum. How the heck could I get to 2? It's not a 2-photon transition. It's 1 photon.
Does it something have to do with the unharmonicity when you make the intensity very large?
It's not one nonlinear effect. It's in first order perturbation. Good guess. Good thought. That would be a 2-photon light transition. Yes, sir. You're allowed to guess.
But your angular momentum of the photon has another part
Exactly.
that can also transfer momentum.
There is orbital angular momentum in the photon as well. Now you may or may not remember that a plane wave is not an eigenstate of orbital angular momentum. It's an eigenstate of momentum, not orbital angular momentum. What are the eigenstates of orbital angular momentum? They're spherical waves. And we can decompose plane waves into a superposition of spherical waves. That, you may remember, is known as the partial wave decomposition, right? Now, we can think about the joint. That's a separable basis. Spherical wave times helicity is like the product basis of orbital and spin. But I can also talk about the modes of simultaneous eigenstate of both, right? That's the coupled basis that you might remember for the addition of momentum. Those modes are called spherical vector or vector spherical harmonics. Chapter 16 or something of that. Jackson. That's what those are. Those are the states of total angular momentum. That includes both spin and orbit. But everyone forgets that photons have orbits. You don't have to just have 1 unit of h bar. You could have 2, or whatever you want. Cool. All right. Now, I learned the way to erase these boards. Watch this. Yay. All right, so now that we have the field, we can now look at the interaction of matter and fields. So, to do that, let's write down a Hamiltonian. Still gonna get my exercise. All right. So, to do that, we begin with the fundamental Hamiltonian. Which is known as the fundamental Hamiltonian is, I'm going to write it, it's called minimal coupling. And we'll write it as following. H. Well, we have a bunch of charges. So I'm going to have point charges with charge Q sub J, for whatever the J charge, and mass of the charged particle. So these could be, say, electrons and protons, or electrons and nuclei, or whatever charges we have. So I'm going to treat the charges non-relativistically to start. So I have the kinetic energy of all the masses. And then I have the interaction that looks like this. P. Oh, I'm sorry. Excuse me. The minimal coupling, I have to write the canonical momentum. So we're in the Coulomb gauge. We have the kinetic term, which involves the kinetic momentum, which, as you may have learned in your quantum mechanics classes, means I have to be careful. The thing that there's the canonical momentum and kinetic momentum, and they're related in this way. And then I have the term that I ignored in the past in the interaction. And then I have the Hamiltonian for the field. So this involves Hamiltonian for matter, the Hamiltonian of the field, and the interaction between these guys. This is the position of the charges, which in quantum mechanical terms are operators. Okay? Right. Firstly, as we discussed, we're going to ignore, though it has, because it has zero effect on any of the dynamics, we'll forget about the 0-point energy. It does nothing. Okay, so that's the fundamental Hamiltonian. But in quantum optics, we're interested not in high energy modes of the electromagnetic field. We're interested in the near resonant effects that couple the photons to energy levels that are separated by something like optical frequencies, maybe ultraviolet, but we're not going beyond that. So for low energy photons, the wavelength 2 pi over k is much, much bigger than the size of the atoms. And in that case, we can make a multipole approximation. Now, to do that's a little bit complicated, and I actually meant to say this, I got buried underneath my iPod, is I wanted to say if you're really interested, and I'll put this is mentioned in the list of references. This text, which came out when I was a graduate student from the famed Claude Cohen-Tanucci and co-workers, is a great reference for talking about all the fundamentals of the quantization of the field from a quantum optics, not a high energy physics perspective, and talks about a lot of the details that I'm sloughing over here, like what about the longitudinal photons? Aren't those photons? This is a great reference. So if you're, I would see what you can find on Amazon. Get a hold of this if you're interested in the fundamentals of quantization, low energy perspective. Right. So we make the multipole approximation, and in particular, we'll restrict our attention, even though I said we didn't always have to do that, but for simplicity, and the cases we care about the most, the dominant term with neutral atoms is electric dipole. So, in the dipole approximation, our Hamiltonian now takes the following form. Sum over all the charges still have whatever the scalar and potential is, minus the dipole dotted into the electric field. We'll actually write it like this. So that's the electric dipole approximation. In the electric dipole approximation, the interaction term, this is the atom field interaction, involves the electric dipole sum over the charges like that, right? That's the electric dipole operator.
Where's A?
A became E when we went and did the multipole approximation, which I didn't, just not worth it. Okay. And this is at the center of mass. this is the Hamiltonian of the field. And this is the Hamiltonian of the atom. Right? It could, for example, be a hydrogen atom, in which case I would have the kinetic energy of the proton, the kinetic energy of the electron, and this would be the Coulomb interaction that wouldn't involve. So let's just write that down just for, so for example, in hydrogen, the Hamiltonian of the atom is the momentum of the proton square the kinetic energy of the electron, and then the Coulomb interaction. That looks at the relative energy, right? That would be the hydrogen atom. Yes, sir.
Probably you want to include the charge in that last term. Oh, no, D is, never mind, sorry.
Yeah, D has this is the dipole.
Sorry.
Yep, no worries. Right? And of course, this, we write it, we separate into relative and center of mass coordinates. This gives us bound states. Okay. Now, the center of mass position of the whole atom, typically we don't quantize unless the whole atom is very cold, in which case we might have to think about the de Broglie wavelength in atom optics of the whole atom. But typically, we just don't worry about this part and say we're looking at the frozen atom picture where the atom is just at a fixed position and forget about those degrees of freedom. And just for the, I mean, that would give rise to a Doppler shift, but we're not going to get into all those details. We'll just forget about the motion of the atom, keep the atom fixed at some position, and then the energy levels of the atom are related to this. Okay? All right, so with that said, we now have our Hamiltonian, which will be written as follows. The Hamiltonian is the Hamiltonian of the atom plus the Hamiltonian of the field plus the interaction Hamiltonian. The Hamiltonian of the atom, well, I can think about this in terms of the energy eigenstates of the atom. There are bound states. And then there are the unbound states. That's just an energy diagonalization of the atom, right? That's just writing it in its basis of energy eigenstates. The energy Hamiltonian of the field is sum over the modes. A. And the interaction Hamiltonian is minus D dot E at the center of mass. I'll just call that capital R. we don't quantize in the current formulation. Okay, so far we have made the approximation that the atoms are moving non-relativistically, in which case we made a multipole expansion, and kept only terms up to the electric dipole moment. We made what's called the electric dipole approximation. All right, now what? Well, what we are interested in here, what we are going to be interested in, is when we shine light, including the quantum aspects of it, near resonance between two bound states. So we have two levels that we're going to consider that we, as always, call G and E, separated with some energy such that this is the resonance frequency. In that case, the Hamiltonian of the atom is just restricted, as always, to those two energy levels. So this whole mess that involved, all this stuff is now this. All right? Which in our pseudo-spin picture So we make our usual pseudo-spin for the two-level atom, where spin up is excited and spin down is ground. And we always choose it that way. I don't care what atom pump says. This is the way it's defined. There's no ambiguity whatsoever. All right. So that's our two-level atom, right? Everyone agree? All right, what about the dipole operator? Well, the dipole operator written here now, when restricted to this two-level system, as we have always said, that operator restricted to this basis only has off-diagonal elements. This matrix element we call DEG. This is DGE, which is generally the complex conjugate, but we're going to take it to be real. We can always do that by a choice of phase of the rate functions. And so this becomes the vector DEG, sigma plus sigma minus. Very good. All right, so now let's look at the interaction Hamiltonian. I need to add 5 minutes to the class and to raise the damn boards.
If you raise up both boards, you should just have a third board to write on.
Can I put these guys all the way down?
You can lift them all the way up.
All the way up? I see. Good. All right. Good to know. I will remember that for the future. Let's finish this guy to start. All right, so we have the two-level atom. We have our harmonic oscillator through the field and the dipole interaction. I'm also going to have to be more conservative in my use of board. All right. H atom plus H field plus H atom field. H atom field is equal to minus D dot E, which is equal to minus sigma plus plus sigma minus, I'm going to write it like this, DEG dotted into E, sigma plus plus sigma minus. By the way, I'm working in the Schrodinger picture. Now I have a question for you all. Do sigma plus and sigma minus commute with A and A dagger? What do you think? Yeah, because they're different degrees of freedom. So operators associated with different degrees of freedom commute. In the Heisenberg picture, you have to be careful because field and matter degrees of freedom get coupled together with time. So they only commute at the same time. If they commute at the initial time, which they do, then at any later time they commute at the same time at different times. And I'm very careful. That's why I can put this on this side with carefree way. Okay, so now I want to plug in for this. I'm going to write E is equal to E plus plus E minus, where E minus is the conjugate of E plus. And E plus, I'm going to write in the following way. It's the sum over the modes, square root of 2 pi h bar omega k, A of k and lambda u k of lambda at the position of the atom. Okay, so this is at the position of the atom. This u is any orthonormal modes, for example, our plane wave modes. But they could be other kinds of modes we like. So we had for the plane wave, this was epsilon e to the I k dot x over root b, right? For plane waves. So, with that said, I will write this in the following way. This is going to be equal to the sum over the modes, something I'm going to call G, and this is a true annoying feature of so what I have done here, I have defined h bar times g sub k lambda as minus deg dotted into the square root of 2 pi h bar omega k u k lambda. Question for you. What are the units of this thing I've called G? Frequency. How do you see that? Yeah, because this, I mean, and does it make sense? Is the right-hand side? This is an energy then. H bar times G is an energy. Is this an energy? Well, it's a dipole times an electric field. D times E is energy. This is the electric field of that associated with that mode, right? Because if I put in this as the square root of V, that's the electric field, right? D times E. So G is a frequency. It's a coupling frequency. So H bar times is the coupling energy between the matter, the dipole, and the field. All right. Very good. So, now what I want to do is, so let's just say that my fundamental Hamiltonian, my Hamiltonian quantum optics electric dipole approximation, two-level atom, we have this Hamiltonian associated, and then we have the free field over here, and the atomic Hamiltonian over there. All right. What I want to do now is look at the interaction Hamiltonian, not in the rotating frame, because we don't have a rotating frame. There is no driving field with a fixed frequency to which we go to that frame. So that's not, we can't do that. But what we can do is go to the interaction picture. So you may remember in the interaction picture, operators evolve according to the free Hamiltonian. In this case, the free Hamiltonian is the free atom and the free field uncoupled from one another. So that's sometimes called H0. And the operators evolve according to the free Hamiltonian. So in the interaction picture, how does the A evolve if it's a free field?
Either the IH free on one side times
Yep.
either the negative IH.
So we could do that. And do you remember the answer? If I have just a harmonic oscillator, how does the complex amplitude, which is this, evolve as a function of time? It's like a harmonic oscillator, right? This is like the complex amplitude. Has it evolved?
A rotation.
E to the minus I omega t. Learn it. When I don't say this is at times equals 0. Okay, that's true. And similarly, as we did, and I won't do it again, for this guy, now evolving according to this Hamiltonian, going to this guy goes like sigma plus, or I should say sigma minus. It's like the lowering goes like e to the minus I eg in the free evolution. Doing. So, in the interaction picture, my interaction Hamiltonian is equal to the following. The sum over the modes let's use this magic board that we found. That is, we don't have to erase it. All right. So let's just write out all four terms. So that's just multiplying out all four terms. Notice, so these terms, if the mode is close, has a frequency close to this, involves resonant effects. And these are anti-resonant effects. These were the terms that when this was the laser frequency and we tuned it right to what we called the co-rotating terms. And these were the terms that we called the counter-rotating terms in the rotating wave approximation. Now, in the context of thinking about this from the point of view of the quanta of the electromagnetic field, we can think about the effect of these terms from Feynman's perspective of perturbation theory, of elementary processes that occur in different orders of time-dependent perturbation theory. So from the point of view of Feynman diagram, I guess I can't move that one, so. We have Feynman picture. Feynman diagrams. The elementary processes correspond to terms in the interaction Hamiltonian. This corresponds to annihilating a photon and raising the atom from ground to excited. This corresponds to creating a photon and lowering the atom from excited to ground. But these terms, so let's first, we have this term. I'll call this A, this B, this C, and this D. So let's first look at process one. From a Feynman diagram point of view, let me use the following picture. I'll say that the ground state is a line like that, and the excited state is a thick line, that's blue. So I go from ground to excited, and I wish I had another color, but I don't, so photons will be black too. Photons are typically called gamma in Feynman diagrams. So that corresponds to absorption of a photon going from ground to excited. That's process A. Process B is the opposite. I start in the excited state, I emit a photon, and go to the ground state. But what about C and D? How the heck could that be possible? So in C, I, for example, start in the ground state, or I start in the excited state. Let's start with D, because I want to do that one first. I start in the ground state. I go to the excited state. I emit a photon. Is that possible? Well, I can't do that alone is not a good process, but it's certainly an allowed process if ultimately that photon gets reabsorbed and I go back to the ground state, emitting a virtual photon. So this is process D, and this is process C. In process C, I go from the excited state to the ground state, absorbing a photon. So, these effects are there, and what they correspond, these are contributions. What this says, these kinds of processes imply that the eigenstates of the total Hamiltonian that involve both atom and field are not the bare states, but the states that involve the interaction with the quantized electromagnetic field. There is a shift to the ground state energy. This is a second order perturbation. This is a shift in the ground state energy due to this one particular Feynman diagram. And that shift in the ground state energy due to the sort of light shift due to the vacuum is known as the Lamb shift, after Willis Lamb. And sometimes the light shift is cheekily known as the lamp shift, because, yeah.
Can you get the opposite process where you absorb the photon, briefly dropping into the ground state and re-emit it?
Absolutely. So that's it. There would be a lamp shift on the excited state. So these effects, this is not the whole lamp shift. We can't get the full correct lamp shift from our quantum optics-y Hamiltonian because we have made the electric dipole approximation and we have ignored all the higher order relativistic effects. But this is one contribution to the lamp shift. And what we do then is just absorb all these counter-rotating terms into a renormalization of what we call the ground energy and excited energy. That is to say, when you may or may not have done this, when you study fine structure in the hydrogen atom, we do it first in the non-relativistic approximation. We get, the Bohr Rydberg levels, whatever they're called. And then we add corrections, relativistic corrections. So just these counter-rotating terms are taken into account as a redefinition of what we mean by the energy levels themselves. And so they don't play a role in the resonant effects, and we make the rotating wave approximation and neglect these, other than their effect on that. So the final conclusion of today's lecture is that we have now in the rotating wave approximation, we keep only the co-rotating terms. And we're done. And this is the fundamental Hamiltonian of quantum optics, of a two-level atom interacting with the quantized electromagnetic field. We have the free field, which is just a bunch of harmonic oscillators. We have our two-level atom, and we have the interaction of our two-level atom with the quantized field in the rotating wave approximation. And we will be taking this through the rest of the academic year. All right. Excellent. To be continued. See you next week.